A very good afternoon to Dr. Matthew Wong, Mr. Liu Tai, and to other viewers that are watching this presentation. My name is Andy Tang, and today I'll be presenting my final year research project topic, the Strut Efficiency Factor for the Analysis of Steel Fiber Reinforced Concrete Beam. So this is a roadmap of my presentation. Before we dive into the topic, we first must understand what is a strut and type model is. A strut and type model is a well-known truss analogy method which helps to idealize the complex flaw of the stresses by using a pin-jointed truss. Strut and type model encapsulate the lower bound plasticity theory and assuming the concrete and steel to be perfectly plastic, and certify the stress equilibrium condition with the implicit strength compatibility check. So from this figure, it shows that the beam can be classified as two regions, which are the D region and B region. A B region, also known as a Bernoulli region, where the stress can be determined according to sectional method. For the D region, also known as a discontinuity region. In this D region, the shear strength dominates the behavior, so the beam theory cannot be used to determine the internal state of stress. Hence, the strut and type model are adopted to design for this D region. And the main parameter that influence the accuracy of the result produced by the strut and type model is the strength reduction factor, also known as the strut efficiency factor. The strut efficiency factor can be defined as a ratio of stress in the strut to the compression strength of the concrete and is mathematically expressed as the following equation. So let's move on to the problem statement of this research. Steel fiber reinforced concrete has gradually advanced from a new, rather unproven material to one which now attains enlargement in numerous engineering applications. Although there are many design codes that propose the strut efficiency factor for conventional concrete, a common model with a standardized strut efficiency factor for steel fiber reinforced concrete has not been achieved due to a little literature coverage. Hence, it will be a significant contribution to develop a strut efficiency factor to design SFRC beam. So the end of the research is to propose strut efficiency factor for steel fiber reinforced concrete from database collection. The objective for this research is to compute the strut efficiency factor for SFRC through the database of experimental results, and to validate and calibrate the baseline model from the filter database through numerical analysis, which we call the vector 2, and to conduct parametric study on the asymmetrical span SFRC beam through numerical analysis to justify the proposed strut efficiency factor for SFRC. So next, the hypothesis of the research is the strut efficiency factor for SFRC will be affected by the fiber factor and cylinder composition of the SFRC. So let's move on to the literature review. So steel fiber is a material that can help to enhance the brittle nature of the conventional concrete by adding adequate amount of steel fiber in terms of fiber content. The shear capacity of the concrete can be enhanced. This figure illustrates that with a high ratio of steroid in SFRC, which will result in ineffective of steel fiber on shear capacity. This is according to Chow 2018. So next is strut efficiency factor. Strut efficiency factor plays a very important role as it ensures there is none of the stresses in the strut and type model element exceeds the allowable capacity. So the table below shows the proposed strut efficiency factor by various design codes, namely the American Concrete Institute SCI 31N and the Australian Standard AS 3600 and also the Euro Code 2 Part 1 2004. The methodology of the research began with the database collection. A total of 72 specimens has been collected and summarized into the table below. In order to determine the relationship between the strut efficiency factor for SFRC with fiber factor and cylinder composite strength, a regression model is developed. So it is noted that the closer the value of R squared equal to 1, the greater the relationship it is. Hence, it is observed that there is a minimum relationship between this variable with a relationship of only 1.5%. In order to achieve the relationship, the specimens are then filtered based on this criteria, namely the strut failure criterion, the completeness of collected data without making any bias assumption, and last but not least, eliminate the suspicious data from the database. Hence, a total of 16 high-quality specimens passed the strip filter. So the graph below shows a comparison between the proposed strut efficiency factor by various design codes and the computed strut efficiency factor for SFRC obtained from the database collection. As we can see, the R-squared value is equal to 82.07%, which means that the red color power trend lines almost perfectly fit the data, and the regression equation of proposed strut efficiency factor for SFRC can be expressed as the following equation. So after collecting and filtering the data, numerical modeling is then carried out. The first step of numerical modeling is to develop a baseline model. Hence, 6 specimens were validated against the experimental log displacement graph by varying fiber content within a range of 0.5 to 1.2%, whereas the cylinder composite strength are varying within a range of 20 to 40 megapascal and 40 to 60 megapascal. And after developing the baseline model, parametric study is then conducted. A total of 24 asymmetrical span of SFRC beam were designed in accordance to STM principle. Three design parameters were varied systematically in this study. For example, the strike angle was designed to the nearest of 30, 45, and 60 degree. The fiber content by volume from 0.5% to 2% with an increment of 0.5%. Last but not least, the cylinder composite strength of 35 and 60 megapascal were used to conduct this parametric study. And a summary table is tabulated in the table below. The proposed strike efficiency for SFRC is computed based on the cylinder composite strength and fiber factor. So next, the result and discussion. This 6 graph shows a comparison for the log displacement graph between the numerical model and experimental result. Beside, the green line represents the theoretical model and is to use to justify the initial tangent modulus for both numerical and experimental results by utilizing the shear stiffness theory. The experimental results shown in the graph in the first column is taken from the Chu and Kim, while the rest of the experimental results are taken from the Narayana and Darwish. The result between the numerical and experimental reflect a high degree of accuracy except for the specimen of C32.13 with 1% of steel fiber content. This might due to differences in the concrete mixture. However, the ultimate shear loss of SFRC and the graph pattern between the numerical and experimental are similar. So to summarize my finding, the plot of 1% of fiber content will be shown as it represents similar performance for other specimens. So based on the graph, the proposed peak log computed from the lower bound theorem of STM is lower than the ultimate log obtained from the vector 2, which justifies that the proposed strike efficiency factor of SFRC is acceptable. Table varies across different strike angles were tabulated and show the peak log generated from vector 2 and maximum log obtained from the lower bound theorem. So to conclude this presentation, the hypothesis has been validated whereas the strike efficiency factor for SFRC is dependent on the fiber factor and cylinder composite strength. As the strike efficiency factor for SFRC increased, the fiber factor multiplied with cylinder composite strength of SFRC decreased. Besides, the proposed strike efficiency factor has been justified based on the numerical and parametric result. Lastly, a final regression equation for computing strike efficiency factor will obtain as given below. For the future work, experimental work can be conducted in order to further validate the proposed strike efficiency factor through the numerical and parametric study. There is some limitation in vector 2. For example, vector 2 is only able to analyze limited type of steel fiber such as the hood and strap fiber. Hence, it is interesting to find out the strike efficiency factor for other type of fiber through experimental work. So that's all for me. Thank you.